Welcome all. Theorem 7.24. If K is a compact metric space and if Fn is an element of C of K for n equal to 1 to 3 etc. and if sequence Fn converges uniformly on K, then sequence Fn is equicontinuous on K. We will discuss the proof. We have the suppositions. K is a compact metric space and Fn is an element of C of K for n equal to 1 to 3 etc. and sequence Fn converges uniformly on K. Now we have to prove that sequence Fn is equicontinuous on K. For the sake, let epsilon positive, and we first use the fact that or our supposition that sequence Fn converges uniformly on K. So by theorem 7.8 we can write sequence Fn is Cauchy, and so there exists an element of a natural number such that norm of Fn of x minus Fm of x is less than epsilon by 3. For our sake we are taking here epsilon by 3 for every n comma m greater than or equal to capital N and for every x element of K. In particular, choosing m equal to capital N, we can write norm Fn of x minus Fn of x is less than epsilon by 3 for every n greater than or equal to capital N. Now we have to only mention the running of small n only for every x element of K. This is the equation number 1. And now we are using the another fact that Fn is an element of C of K for n equal to 1 to 3 etc. And we know that by the definition of C of K that all members of this family is continuous and bounded, and here we are using that Fn is continuous on K for every n. And since K is compact, we know that a continuous function on a compact set is uniformly continuous, and so Fn is uniformly continuous for every n. Now consider the functions f1, f2, etc. fn. We know that Fn is uniformly continuous for every n, and so these functions also uniformly continuous on K. Then by the definition, for the epsilon greater than 0 mentioned above, there exists delta 1, delta 2, etc. delta n such that modulus of fi of x minus fi of y is less than epsilon by 3. For our sake we are taking here also whenever d of xy is less than the corresponding delta I, and this is true for I equal to 1 to etc. capital N. Okay, now choosing delta to be the minimum of all delta 1, delta 2, etc. delta n, we can write this equation is true for every this is true that is modulus of fi of x minus fi of y is less than epsilon by 3 is true whenever d of xy is less than delta, where delta is the minimum of all delta i's for I equal to 1 to extra n. So this delta will work for every I equal to 1 to extra n. This is the equation number 2. Now we are going to the main part, that we have to check the equicontinuity. So we are considering modulus of Fn of x minus Fn of y, and we are adding and subtracting some terms like Fn of x and Fn of y, and by the properties of modulus function we are splitting the terms into 3, and we know that by equation 1 and 2 that each of the terms is less than epsilon by 3, and so we get this is less than epsilon whenever d of xy is less than delta. That is modulus of Fn of x minus Fn of y is less than epsilon whenever d of xy is less than delta, and for every n greater than or equal to capital N. This is because in our equation 1 and 2 that is only true for n greater than or equal to capital N. From equation 1 we can deduce this. So this result is true for only for all n greater than or equal to n, but we have to write it for every n to prove this is equicontinuous, and that is clear by the equation number 2, that modulus of Fn of x minus Fn of y is less than epsilon whenever d of xy is less than delta, and for n equal to 1 to extra n also. So we can write this equation or this result for every n. That is modulus of Fn of x minus Fn of y is less than epsilon whenever d of xy is less than delta, and for every n, that is for every n greater than or equal to n, and for every n less than or equal to n, that is for every n. So this means that for the epsilon we have chosen, we have found a delta positive that will work for every n, that will work for every member of the family. So this means that sequence Fn is equicontinuous on K. That is our theorem. Thank you.